creating quantum entanglement with more than 1,000 atoms simultaneously, and then using this system to predict the observable properties of the atoms through measurement. This kind of experiment may sound like an idea from another galaxy, but according to a recently published scientific study, this once-utopian scenario has now become a reality. In a groundbreaking experiment conducted in Basel, Switzerland, a concept that had long remained purely theoretical was finally put into practice. The researchers demonstrated that the condition predicted by the Einstein-Podolsky-Rosen, or EPR, paradox holds true even at a large scale, involving 1,000 atoms. In other words, the doubts Einstein and his colleagues had about quantum behavior in the mesoscopic scale, the realm between the quantum and classical worlds, have now found scientific validation through this experiment. Let's go back to the year 1935. At that time, the phenomenon of quantum entanglement had only just begun to gain acceptance in physics. Yet, three of the field's most influential figures, Einstein, Podolsky, and Rosen, found the theory incomplete. To express their concerns, they introduced a famous thought experiment that would later become known as the EPR paradox. Imagine you have two entangled particles, one with Alice, the other with Bob. These particles are bound by such a strong quantum connection that, when Alice measures the position of her particle, the position of Bob's particle can be predicted with certainty. Similarly, if Bob measures the momentum of his particle, he gains precise knowledge of Alice's particle's momentum. So then, if Alice measures position and Bob measures momentum, does that mean we now know both the position and momentum of Alice's particle thanks to entanglement? This is exactly where experienced physicists begin to raise their eyebrows. Because such a scenario seems to pose a direct challenge to Heisenberg's uncertainty principle, which states that a particle's position and momentum cannot both be known with absolute precision at the same time. EPR, short for Einstein, Podolsky, and Rosen, pointed out this contradiction and proposed: either quantum mechanics is incomplete and particles possess hidden, definite values before measurement, or the uncertainty principle isn't truly universal. At first glance, this line of thinking from the old masters seemed to corner the younger generation of quantum physicists. But were they really right? That's exactly what a team of researchers in Basel set out to investigate. They tested whether the EPR argument still holds true at the scale of 1,000 atoms. How small is 1,000 atoms? Well, consider this. A single human hair is made up of about 10 quadrillion atoms. So 1,000 atoms is an unimaginably small amount of matter. It's important to note, however, that this experiment was not designed to directly disprove the uncertainty principle itself. Rather, the researchers aim to understand how that principle behaves in systems as large as 1,000 atoms, where the boundary between the quantum and classical worlds begins to blur. To properly evaluate a question like this, we first need to understand that the true language of quantum entanglement is actually statistics. So how can science enthusiasts like us begin to grasp that? Let's imagine we have a pair of entangled photons. We already know that there's a strong correlation between their spin values. That means if we measure the spin of one photon and find it to be up, we can predict, even without measuring, that the spin of the other photon will be down. At this point, we accept that the correlation between them is -1. Now we measure the first photon. Its superposition collapses, and its spin is recorded as up. Then, we measure its entangled twin. The superposition collapses again, and we observe a down spin, exactly as theory predicts. But here's the problem. Once both photons have been measured, their entangled state is gone. There's no more entanglement, and no further measurements can be made on those photons. So, how can we be sure that the observed correlation wasn't just a coincidence? From a scientific perspective, you can't draw a solid conclusion based on just one measurement. Even if the spin directions were opposite, that alone doesn't prove quantum entanglement. To truly verify the presence of entanglement, you need to perform the same kind of experiment thousands of times under identical conditions. This is where the statistical nature of the phenomenon takes center stage. Thousands of entangled photon pairs, all produced from the same source, are measured using the same setup. Each time, the spin outcomes and their correlations are recorded. Now, imagine that, as shown on the screen, we have 5 entangled photon pairs from the same source. We measure the first pair. One is up, the other down. Correlation, -1. Then we measure the second, third, fourth, and fifth pairs the same way. After each measurement, we log the spin orientations. Looking at the results, we see that one group of photons generally has an up spin while the other tends to have down. The overall correlation stays close to -1. To summarize the group's spin tendency, we determine which spin direction occurs more frequently. If more spins point up, we classify the group spin alignment as up. If more point down, the group spin alignment is down. After collecting measurement results from hundreds or even thousands of entangled pairs, we move beyond intuition and into statistically reliable territory. This is the scientific foundation required to claim that a system is truly quantum entangled, meaning that the spins are not behaving randomly, but are linked by the rules of quantum mechanics. Turning to the experimental setup described in the paper, we find that the core of the system is made up of rubidium-87 atoms. These atoms are cooled down to a temperature very close to absolute zero. At such low temperatures, the atoms stop acting as individuals and begin to behave as a single quantum entity. This unique quantum state is called a Bose-Einstein condensate, or BC. Here, thousands of atoms become synchronized at the quantum level. You can think of it as a massively scaled-up version of our earlier example with 5 entangled photons. Once this environment is established, the researchers apply a special interaction to entangle a cloud of approximately 1,400 atoms. By exposing them to the same photon field, a universal quantum correlation is created among all atoms. In this scenario, it's not just pairs of atoms that are entangled. Every single atom becomes collectively entangled with every other atom in the system. This results in about 490,000 different entanglement connections, because that's the number of unique pairs you can form from 1,400 particles. Next, this large quantum cloud is physically split in two. Imagine cutting a ball of dough right down the middle. As a result, two systems emerge, labeled A and B, each containing roughly 700 atoms. Although these two groups are now spatially separated, their quantum entanglement is still preserved. This allows the researchers to perform independent measurements on two macroscopic quantum systems and observe how large-scale entanglement behaves under EPR conditions. The experiment enables direct observation of the effects of mesoscopic, that is, medium-scale, quantum entanglement by allowing independent analysis of both subsystems, A and B. But here comes a crucial detail. The researchers are not measuring the spin of individual atoms. What's actually being observed is the collective spin orientation of each group, the total quantum angular momentum formed by around 700 atoms acting as one. We can compare this situation to the earlier example with 5 entangled photons. In that case, the overall alignment of the group mattered more than the state of each individual photon. The same applies here. For each of the two atomic clouds, labeled A and B, the dominant spin direction of the group is used for measurement. So how is that even possible? Due to their quantum nature, the rubidium-87 atoms used in the experiment can exist in only 2 energy levels. These can be thought of simply as spin up or spin down. To directly measure the number of atoms in each spin state, the researchers used a method called resonant absorption imaging. In this technique, a laser beam of a specific frequency is partially absorbed by the atoms depending on their quantum state. By analyzing how much light is absorbed in a given region, the number of atoms in each spin state can be determined, with an uncertainty of about plus or minus 3 atoms. This allows scientists to detect, in a single shot, the density of atoms in each spin level. As a result, the total spin orientation of each group, for example, the component in the z direction, denoted as SZ, is directly measured. Here's the most important part. This is not about reading each atom individually and averaging the results. Instead, it's a single-step quantum measurement that reflects the collective behavior of the entire group. By precisely counting the number of atoms in both quantum states, a spin difference emerges. For example, if 55% of atoms in group A are spin up and 45% are spin down, then the group's total spin is said to be oriented up, just like we described in the photon example at the beginning of the video. These measurements were repeated many times and from multiple directions, and each time, an astonishingly strong quantum correlation was observed between the results of groups A and B. For instance, when the spin direction of group A was measured at a certain angle, the result from Group B, measured in the same direction, often turn out to be the opposite. And when repeated enough times, this pattern was too consistent to be explained by mere coincidence. One of the most striking findings in the study came after these measurements were analyzed. The results from Group B turn out to be remarkably effective in predicting the unmeasured spin components of Group A. The error margin of these predictions even fell below the minimum threshold imposed by Heisenberg's uncertainty principle. What does that even mean? Well, quantum mechanics tells us that you can't know certain properties of a particle simultaneously with infinite precision. No matter how advanced your instruments are, you can't get below that threshold. That minimum boundary, the floor set by the uncertainty principle, can actually be calculated with exact mathematical precision. So when a new experiment is conducted, scientists can check whether or not that boundary has been violated. But in this case, things played out a bit differently. The spin component of Group A wasn't measured directly. Instead, predictions about Group A were made based on the measurement results from Group B. And those predictions turned out to be so accurate that they surpassed what direct measurement alone could usually achieve. This result appears, at first glance, to validate the famous thought experiment proposed by Einstein-Podolsky-Rosen back in 1935. Thanks to the strong correlations offered by quantum entanglement, it seems possible to obtain information about one system without measuring it directly, simply by observing its entangled partner. But then the question becomes, is this really what EPR had in mind? Let's try to make things a bit more concrete. Imagine a die being rolled inside a box. You can't see the top face, but there's a device showing the bottom one. If the die is fair and the bottom face shows a 2, you know with certainty that the top face is a 5, because the total must always be 7. A similar logic seems to apply here. An unmeasured spin component in Group A can be predicted with high accuracy just by measuring Group B. The authors described this finding as the first experiment to directly observe the EPR paradox in action. But they also made it clear, this study does not claim that the EPR critique was fully correct, nor does it intend to invalidate the uncertainty principle. The results don't negate the fundamental validity of the uncertainty principle, because the spin components in System A were not measured directly and simultaneously. Instead, highly accurate predictions were made using measurements from System B. So the distinction between measurement and inference remains intact. As long as measurements are direct, Heisenberg's uncertainty boundary still holds. But the most remarkable result from this experiment is this: quantum entanglement, even on the scale of 1,000 atoms, can produce correlations strong enough to allow information without measurement, just as the EPR paradox once proposed. This challenges the classical idea of locality and offers a powerful experimental confirmation of the deeper nature of quantum mechanics. And yet, as a curious reader, I must say, even the conclusion section of the paper felt somewhat incomplete. Let me explain. Imagine that I perform a highly precise position measurement on System A of an entangled pair. At that moment, the superposition collapses, and I can no longer measure A's momentum. Still, I have the exact position of System A in my pocket. Meanwhile, System B, which is entangled with A, has its momentum measured. And using the known entanglement correlation, I derive the momentum of System A based on that of B. Doesn't that mean I now know both the position and momentum of System A? Isn't that, by definition, a violation of the uncertainty principle, even if it's happening in a system of 700 atoms? If you enjoyed this video, don't forget to like it, leave a comment, and subscribe to our channel. Your support helps us reach more curious minds like yours.